Hi everyone. Today we have Miguel from Nillion. So hi Miguel, welcome to FHE on Chain.
Hi, Remi. Thanks for
Yeah,
having me here.
yeah, absolutely. I guess to start off, would you like to talk about more about your background? Introduce yourself.
Yeah, so very briefly, I am the CSO, so the Chief Scientific Officer and co-founder at Nillion. And I guess my background is at the intersection between engineering and maths. So I've done a master's degree in telecom engineering, but also a PhD in maths. And I've been working for almost 25 years in distributed systems all along my career.
Very cool. So maybe just to start, how would you introduce Nillion? Just kind of like from a high level.
So the first thing that comes to your eyes when you look, when you go to Nillion.com is it's a blind computer. So we're building a blind computer, and what that means is that first of all, if it's a decentralized network, so we're not talking about one single computer. It's like a metaphor. So it's a network of nodes and computers, and it is decentralized. So it's unlike the current internet, which is pretty much centralized. And the main feature of this network is that it's meant for secure storage and compute over high sensitive data. So that is again in contrast with the current internet where you can store information in encrypted form and then transfer it in encrypted form. But if you want to compute on it, you need to decrypt it first. So we are talking here about covering the whole cycle of storage, transmission, and computation in protected mode. So without having to decrypt or open or reveal the information. And when you compare it to Web3, I guess other Web3 technologies like traditional blockchains, blockchains are decentralizing transactions. Here we're talking about decentralizing computations themselves.
Yeah, this is very cool. I like the term blind computation. I think it's a very clever way of naming this. So
Yeah,
Ni-
it's very descriptive.
Nillion, given it's yeah. Uh, Given Nillion is, a multi-party computation system, and then, I mean, the end result is very similar to, what FHE tries to achieve, which is computation on top of encrypted data. Um, would you like to maybe talk about, why is FHE considered a type of MPC?
Yeah. So maybe we can talk about what FHE means and what MPC means. So FHE in its most basic form, like you said, it's about computing on encrypted data, but it kind of follows a client-server architecture. So I'm a client, I have some data, I send it in encrypted form over to you, and you're a server, and you compute on my behalf some function or program, and then you give the ciphertext from the result back to me, and I decrypt it. That's kind of the most basic setup for FHE. MPC, what it means is that now we're not one client and one server. We are a network of computers, and we want to jointly run or compute some function of our inputs and come up with a result. So you have the element of of a network. That's the main difference. But as it turns out, with FHE, you can actually shift it from this client server architecture into the other notion that I've described by simply adding a threshold scheme to the private key, so that there's no one party or one node that owns the private key, but rather it's kind of cut into pieces, and it is all of the nodes in the network that have shares or parts of that private key. And now suddenly you have MPC that is built on FHE. And in fact, there are other ways of building MPC as well. So the three main ones are FHE, also linear secret sharing, which is a way of also kind of sharing information amongst a number of parties. And maybe Shamir secret sharing is the most famous example, and also garbled circuits. So those three ways are kind of different ways of building MPC, but FHE is something more than that in a sense, because it not only serves as a building block to MPC, it can also be its own client server solution for more traditional use cases.
Mhm. Maybe just for the audience, maybe we can use Yale's millionaire's problem to illustrate, the form factor between the difference between the form factor between FHE and MPC for the same problem.
Yeah, that's a good idea. So okay, so that problem is a famous one. It's the first one that was solved in secure computation, and it's about two buddies. They are millionaires, and well, it can be extended to more than two parties, but let's say it's two people, and they want to find out who is the wealthiest one, but they don't want to reveal their wealth. So that's the catch, right? They just want to learn one bit of information, which is either you or me is the richest one. So how do you do that? This is a comparison, but a comparison that runs on private inputs. So the wealth, the number of, you know, the amount of money that each one has, that has to be kind of protected, and then the comparison needs to output one bit. So essentially, we could think about maybe three scenarios. So in one, we have the client server FHE setup that I just talked about. So in that scenario, the two millionaires are clients, and they send their ciphertext over to a server. And then the server computes the comparison, and then it gets returned back to the two millionaires for decryption. The problem here is that both have the decryption key, and so both would be able also to decrypt the inputs if they had access to the server. So it's not completely a secure setup in that sense. So another scenario is that you use a blockchain. So in that scenario, you're still using FHE. You still are sending the ciphertext this time to the blockchain, and then everyone can compute, the comparison, and maybe there is a designated node that is entitled to decrypt that, or maybe you want to kind of secret share or thresholdize the decryption key so that only when everyone is ready to decrypt the result can they obtain that result. But then you're talking about now moving to the next step, which is MPC. In its most general form, MPC requires the nodes to be also compute nodes. That's kind of the way it's done in the literature, although you can also outsource the computation to a network. But let's say in the example by the book, the two millionaires would be also compute nodes. So they would be exchanging some information regarding their inputs, their wealth, but this wouldn't reveal anything. And then they would be collaborating and doing a computation of this comparison, and they would be able to reveal the result for them. So this is the theory. As I said, in practice, usually this computation is outsourced to a network, which is what we do at Nillion, so that the nodes or the millionaires just become what it's called dealers. They just produce or contribute with inputs to the computation, but they don't actually run any computation.
Yep, and yeah, correct me if I'm wrong. The way I see the major difference is in threshold FHE, all the computation can be done by a single server, and then the decryption is done by MPC. In the MPC system, essentially each ciphertext is split across many nodes, so they're all partial computations across multiple nodes, and then the answer is reconstructed at the end. That would be kind of like the major difference here.
Yes, although with garbled secrets, you have something that resembles the FHE way of doing things, because you encode, rather than encrypt, you encode the inputs, but also the secret. And now the evaluation of the secret, of the encoded secret, can be done also by a single node. But then also the decoding is thresholdized, so to speak, so that only the community of all the nodes can then reconstruct the result. But in that sense, garbled circuits could resemble FHE in that the computations could actually take place in just one node instead of what happens with linear secret sharing, which is what you described, that the community of the nodes is the one actually collaborating and running the computations.
Mm-hmm. Maybe talk about some of the trade-offs that you see between MPC and FHE, generally speaking.
Yes. So essentially, I think we can think of it in terms of three different dimensions. One is communication complexity, and that is how many rounds of communication do the nodes need to have. So usually, in some MPC flavors, they require to communicate, and so this measure counts the number of rounds. You also have bandwidth complexity, which counts the amount of information that the nodes need to exchange in those rounds. And then you have computational complexity, which measures the local computational effort or cost of running that computation, in terms of CPU or GPU usage. And the interesting thing is that these three flavors I've mentioned, FHE, garbled circuits, and linear secret sharing, so those three ways of building MPC, they score differently in this three-dimensional grid. So FHE, for example, let's talk about the Achilles heel, for example. So FHE scores the worst in computational complexity, so it kind of puts the burden on computational complexity. Garbled circuits puts the burden on bandwidth because it has to encode the whole circuit, and that can be huge. Whereas linear secret sharing scores the worst typically in round complexity, so in the number of rounds of communication. So what you have is that actually the different flavors are complementary in that sense, performance-wise. And when you go even beyond MPC and secure computation and FHE, and think about, for example, ZKP or other PETs, then you also have complement. They are also complementary, but this time on the functional plane, because they just do different things. And also maybe at a more detailed level of comparison between the different FHE and MPC solutions, you have other things like pre-processing. So that's a big difference between MPC and between FHE and other MPC solutions, which is that for FHE, you don't need pre-processing. So pre-processing is a stage that is prior to the users being there waiting for computations, but it's about preparing some randomness so that things go smoothly and efficiently when users come in. But of course, this complicates the management of the network, and FHE doesn't require that. So it's a very good point in favor of FHE. But you also have other things like active security. So with FHE, it's more difficult or costly to achieve active security, which means it's a very high or special form of security that protects you against the nodes deviating from the protocol. So it's like the worst case scenario where the nodes are not just trying to find and learn the secrets, they're also kind of going rogue and doing whatever they want. So you could end up with computations that are not correct. So with FHE, you probably need to either replicate the computation and then run consensus on the result, or run, the computation is run by one node, but then you need to verify that computation. So probably you need to generate a proof of execution via zero knowledge proof. This all costs, time and resources. With linear secret sharing, for example, that comes in more naturally because it's built in with error correction codes, and it kind of resembles more what happens in a blockchain. So those are just two examples that says that actually, this is a more nuanced question, the comparison of the different PETs. It is a complex trade-off space. It's not just about the three axes that I mentioned, but definitely there is this notion of PETs being complementary, both on the performance side of things, but also on the functional side of things.
Yeah, I think this is a pretty comprehensive comparison and just, talk, comparisons on the trade-offs. I guess here we can introduce kind of the topic of orchestration layer that Nillion is building. Would you like to maybe talk about how you guys are thinking about these trade-offs, and then how you're choosing different primitives for different specific operations or use cases?
Yeah, sure. So one of the key components of Nillion is what we call the orchestration layer, and it responds more or less to what I was saying before, that there is no silver bullet in PETs. They are complementary, both performance and functional wise, But nevertheless, what we find nowadays is that PETs is a very fragmented space. So there's different communities, some of them working on this corner of things, some others on this other corner of things. And this makes it very hard for a developer to come in and combine different PETs in the same place. And you also have challenges around interoperability, both in terms of data and computation. So just moving data from, for example, ciphertexts over to secret shares is something that is not typically provided by networks. So as a result from this, as a developer, you find it hard because you have to do all the plumbing yourself. and you have to understand these complex trade-offs between costs and security and performance and maturity and expressivity of the different PETs. And as a cryptographer, it's also challenging because you have to not only come up with a new protocol, you also have to find ways to benchmark it. You have to, deploy it on a real network and find nodes who run this protocol and secure them with SLAs and, incentivize them, find ways to pay for the costs. And you need to deploy the infrastructure. So this is getting very challenging for researchers as well. So the idea of orchestration is about destroying all these silos, removing these barriers, connecting the different PETs and their data. It's about providing tooling for these developers and cryptographers, making their lives easier, so to speak. And it's about also aligning their incentives so that they all contribute to this ecosystem. It's about also making the ecosystem larger by destroying those or by building bridges between the different PETs. And I think a good analogy is that of a maestro. So this maestro is conducting in an orchestra, and you have different cryptographic techniques playing in that orchestra as different instruments, and you can add more and more instruments and play more complex pieces. So it's just it's a scalable approach in that sense. You don't need to start with all the landscape of PETs. You can start with one and then add a second one and then so on. So it's naturally you start playing from very simple pieces to more complex compositions. And then it's also a very flexible approach because it acknowledges, we think, the fact that PETs is a very active area of research, and they're going to keep on innovating and creating new PETs as while infrastructure is being built. So it's not going to be like, oh, now we freeze, we stop innovation, and we're going to build that into our infrastructure. But rather, this is going to be like a continuum of new ideas and versions and variants of PETs coming in. And so your infrastructure has to be built to accommodate for that reality.
Got it. So you're a aggregate of PETs, and then it's also open-ended to accommodate newer PETs down the line to be part of this orchestration.
Yes, the idea is that we become modular and we allow for different PETs to connect to our orchestration layer, and then the orchestration layer is essentially facilitating that interconnectivity, that connection, those connections between the different PETs.
So one year end developers write a program on Nillion. So what happens behind the scene is this maestro setup that you described, right? So they don't know necessarily which PETs they're using behind the scene, but this is kind of like all abstracted away. Is that correct?
Yeah, there's different levels. I don't think there's going to be like one level replacing the other. I think they will coexist in time. So the final vision is what you say. That's what we call level 4. It means that as a developer, you don't need to understand necessarily about PETs and that complex trade-off space. You just see different data types, integers and fixed point arithmetics and whatnot. And under the hood, the orchestration layer, or the compiler in this case, is kind of choosing the best combination of PETs, factoring in the cost of conversion between different PETs to provide you with the best solution. What best means depends on also what you're interested in. So you could be interested in minimizing cost, or you could be interested in performance, you could be interested in security. So you do have to provide some notion of what is best for you. But beyond that, most of the work would be lifted or done by the network. But there's 3 other stages as we see them, or levels. So level 1 is essentially the different PETs are like libraries, and inside it's like a black box. You don't see what's going on inside, and yet as a developer you're able to connect with them and use them. Second level is when they become first-class citizens in the language, in the native language that we have, and that means that you can refer to them not via library external calls, but actually via casting operations inside of your language. So the different PTs are represented as data types, and you can switch between them through casting operations. And level 3 is like a previous step to level 4, where we're grouping some of those PETs together. For example, all FHE flavors could be grouped in one FHE, integer type, FHE bit type, FHE fixed point type, and then under the hood, you're switching between the different FHE flavors, but you're doing that automatically. So the developer now no longer needs to know, okay, I'm going to use TFHE or I'm going to use, CKKS, or I'm going to use something else, but rather that's done automatically. And other groupings would be, for example, two-party protocols could be grouped together, or for example, all protocols with passive security could be grouped together, things like that. So it's like an intermediate level between levels 2 and 3 and 4. And I don't think that this is we're going to see like, oh, level 4 is going to replace everything else. I think at any given point in time in the future, we'll have certain protocols in each one of the levels. So newcomers to the platform will start with level 1. If there's demand for those protocols, then probably they will be incorporated into the language for level 2 and so on. So if they become more famous and useful, then we will elevate them to levels 3 and 4.
Yeah, this is very interesting. So you're taking a very iterative approach as well to see, which PTs has more demand, which ones are maybe becoming obsolete, getting replaced. Super interesting.
Yeah, I think that's a key element, right? We're not trying to be prescriptive or like trying to guess the future. We don't know. So whatever the market demands, that's going to be favored. But at the same time, this is a very ambitious vision. So we wanna structure it in a way so that it even makes sense to play an orchestra like of just two PETs, to start small at the beginning.
Yeah. Maybe just to compare, let's say like a FHE blockchain and a MPC protocol, the differences on the way things are stored, how the private states are stored, computed.
Yeah,
you can go deeper on that.
That's a very good question because they're, I think, fundamentally different. So, for example, in a FHE blockchain, you have this global state, and you need to get consensus on the value of that state. In an MPC network, you're slightly more flexible. So the way Nillion Network is structured is it has different subnets or clusters. And each one of those clusters is pretty much independent from the rest of them. So you don't need to reach consensus on the state of the different clusters. You just need consensus intra-cluster. And by consensus, I mean agreement on, let's say, the result from a computation, so on data. But then again, the different computations are independent. So if I'm running a computation on one cluster and you're running another computation on that same cluster, the cluster nodes don't need to kind of, agree on the superset of the results from my computation and your computation. We just need agreement on my computation for me and your computation for you. And so those clusters are pretty much independent. And also what you then need in terms of a global consensus is like agreement on a meta state. And that meta state is more or less, number one is about payments. So there is a blockchain and you need some consensus, of course, on the token that runs those computations, but also it's about those operations that are intercluster. Like, for example, if I have some secrets in one cluster and I want to move them over to another cluster, so that will require the coordination of the two clusters. And that's now an operation that needs to be elevated to a blockchain type of infrastructure that is able to agree on the fact that those secrets were consistently and correctly moved from one cluster to the other. So most of the time, we don't care about global consensus. The clusters run independently. But in some occasions, we do need to have certain, like more traditional notion of consensus, like a blockchain would.
So I do see one trade-off here, which if you're a blockchain, your nodes could be easily replaced, or you can replay all the transactions all the way from Genesis and recover all the all the data back, right? in this MPC system, is there a similar type of structure where the system becomes a little bit more fault tolerant or just anti-fragile? Basically, if something were to happen to some nodes, you'll be able to recover all the way back from Genesis or recover all these private states.
Yeah, that's a very good question. So in MPC, in those clusters, MPC protocols have they have one limitation, which is that they have to be pretty stable in terms of the number of nodes that are inside of those clusters. You can grow in terms of number of nodes or change, reduce that number of nodes, but that has certain cost because now those secrets that were shared amongst, let's say, 10 nodes, now they need to be shared amongst 15 nodes. And that is an operation that requires some communication and some computations going on. So it is true that those clusters are in principle more stable than what you would expect in a normal blockchain where you can add and remove nodes more fluently, so to speak. What you can do fluently is to add different clusters, so the subnets themselves. At that level, you can add them and remove them very efficiently. And also, if the clusters are providing active security, then you do have certain flexibility because it means that a certain proportion of those nodes can be offline, can leave the network, and then new nodes can come in without incurring in the cost of those expensive operations that are otherwise needed if the clusters are just providing passive security. So in that sense, those clusters with active security resemble more regular blockchain, but still there are some limitations or some penalties paid when you want to grow like big time in terms of the number of nodes in that cluster. But because of because the results are not like global, so we're not reaching a global consensus on the different results from the different computations, then you can fine tune what degree of guarantees you need for each one, for storing each one of the results. So if you do need a lot of guarantees, then you would go for a cluster with a lot of nodes, and there you have guarantees that, even if a certain portion of nodes goes down, you will still have your result recoverable. But if your result is more like, oh, I want to get this result and just forget about it, then you can go for smaller clusters. So it really depends on the use case that you're after.
Yeah. Kind of curious how Nillion is thinking about this. So it sounds like you will offer different pockets of networks with different sizes. What's roughly kind of like the lower limits and upper limits of the size of these networks that you see?
Yes. So the very lowest limit is 2 parties. So that's the minimum. It provides certain protection. So, against collusion, against, one party from finding out what the other one has, unless they collude. But more typical numbers would be in the tens of nodes. So it could be all the way from 2 to, let's say, less than 100. You would have in certain occasions clusters if the occasion requires it with more nodes, but that's kind of our range, working range. In principle, that's what we're envisioning. And then different clusters can have different also hardware requirements. So some of them, if they're running, for example, FHE computations, they will have GPUs and more expensive equipment. If they run linear secret sharing, maybe that you want to have the different nodes closer, geographically speaking. So maybe they're going to be in the same area or region, geographically speaking. Also, some clusters you will want for data protection purposes, that all the nodes are in Europe or in Japan or in the US, so that you comply with the different data protection regulations. So there's going to be like very different requirements coming in from very different angles, like legal, performance, and so on. And we want to accommodate for all those by just providing with a very flexible infrastructure capable of solving for all of that.
Yeah, I think this is a very interesting point, which is you can really adjust on maybe the risk factor depending on geographic location, the size, the type of machines that you run. And so you want to make this a bit more flexible to leave it to the end consumer to pick. It's like the types of networks that's the most suitable for their use case or application.
Yes, That's
And,
I think
mhm.
that's what you see with in Web 2 with privacy enhancing technologies, which are the traditional ones like encryption. What you see is that the use cases are very different, and so what you need is a very flexible platform that is able to accommodate for all those use cases, and that's the main reason for the orchestration layer as well. If you want to grow the market of PETs, you kind of need to offer the whole range of possibilities together, because otherwise you are going to be restrained and constrained to the abilities and capabilities of a very specific PET instead of what the whole
Mhm.
superset is able to do.
And do you see a world where, Nillion's MPC network could, compose with existing FHE blockchains, like Inco, for example, and provide decryption services, so repurpose the MPC network to support FHE decryption, things like that?
Absolutely, absolutely. That's a very interesting use case. So you can either serve FHE setups with private keys, so where the same private key is used for encryption and decryption, or even public key setups where you have a public key for encryption, but it's the decryption that you want to run in an MPC protocol. And you can also run the key generation part as an MPC protocol. And that's definitely a very interesting and very powerful combination of the two technologies, because on the one hand, FHE removes communication, removes pre-processing, but on the other hand, MPC is giving you the ability to work with a collection of nodes instead of just one node, so that you're running operations under consensus, so to speak. That's a very interesting use
Mhm.
case.
So, if people come to Nillion today, what are some of the use cases that you see people build, and also which ones are you personally, most interested in?
So MPC in general has been very strong on custody with signatures. That's a very kind of it's a use case that fits very well with what MPC can do. We are as a company interested and excited about voting for DAOs. In DeFi, we're very interested in encrypted order books and other related applications like private auctions or private limit orders, or even private trading policies where you're trading according to a set of rules, but that set of rules is kind of private and hidden from the rest. In the health sector, there's a lot of applications starting from private analytics, and that's kind of low-hanging fruit. But you can also think about other things like, even supporting research, because now you can mix databases from patient information, but you're not actually exposing that information, and you can mix and find trends and things like that. Also, supply chains is a very interesting area where you have different companies working together. They're mutually dependent, but they don't want to share information, but they need to because they want to optimize the functioning of that supply chain. AML, anti-money laundering, and fraud detection is also an interesting one, and identity related solutions as well. So, for example, biometric authentication, where you're not exposing your biometric information. That is very sensitive because those are things that once if they're leaked once, then that's it. You cannot change your face, you cannot change your DNA. So that's a very sensitive area that we're very interested in. And then one of the things that we've been working for the last couple of years is AI. And now with LLMs pushing so hard, and the prospects of having personalized AI, which is a future version of LLMs that they become your personal assistant and they know everything about you, your emails, and everything that you do, everything that you've said. They become your therapists and all of that. That I think is a use case that is probably not low hanging fruit, but it's nevertheless very interesting and very important. I think is the use case that is going to put PETs to the challenge, because it's going to be required. We're going to have to use PETs for that use case if we want to protect ourselves against a future where a few companies have more information about ourselves than than what we've seen before ever. like at a different scale. We're not talking about cookies, and we're not talking about, oh, my, search history. We're talking about everything that makes you, being exposed and being given for free to companies. That's very serious. So we think that PETs are really important in this context. And it is in this context that we've started working on something called the discrete wavelet theory and its applications to the acceleration of inference in LLMs.
Yeah, maybe could you give a high-level introduction of what discrete wavelet theory is, and then what sorts of applications? You mentioned inference, but yeah, maybe just expand a little bit more on how
Yeah.
you use it. Yeah.
So they're very well known in functional analysis and digital signal processing. They're kind of wavelets are twins of Fourier transform, but they have the ability to operate as a mathematical microscope, which means that you can, if you have something complex like a function, you can zoom out and have like a simplified version of this function. And it's an approximate version, what you get when you zoom out, because you lose some resolution, some information. But if the function is smooth enough, then that's actually a very good substitute or replacement for the original function. One example would be like a picture of the sun. So that picture is full of nuances like the spots and the storms in the surface. So if you zoom out, you're going to lose information. But instead of that, if what you have is actually a circle, just the line and everything is white, then you can see that when you zoom out, you have still a circle with all the information. It's just that it's smaller. So that is the type of smooth function that is very interesting to work with in wavelets. And what you get is a simplified version of your problem. So now you're working with this smaller version of the function. And that means that all the solutions that you implement on the cryptographic side of things are going to be cheaper and are going to be faster. So that's why wavelets, we believe, are so interesting when it comes to machine learning in general, because you have to deal with non-linearities that are hard to implement with cryptography. For example, GELU in LLMs, but you also have like 1 over x or 1 over square root of x or exponential function. All those functions are smooth, but they're hard to represent as a circuit. So this technique opens the door, for an implementation based on lookup tables that is very efficient.
Yeah, I can see this in the context of machine learning because, like you said, there are approximations, but I'm sure you can also train the model to absorb all of these approximations in the case of machine learning. So now that you mentioned lookup tables, it is a concept that's also present in FHE with programmable bootstrapping. Would you like to maybe discuss how DWT can potentially be implemented within FHE or be used as a potential alternative?
Yeah. So yeah, exactly. DWT is more like a framework existing, a little bit agnostic of the underlying privacy enhancing technology. So it can be implemented on TFHE, for example, using programmable bootstrapping as a technique to evaluate the lookup tables, or it can also be implemented on top of linear secret sharing based MPC solutions. So for TFHE example, what it essentially does is it reduces the size of the lookup table. The size is the sensitive parameter because it's the thing that makes lookup tables not scale well. So for example, if you're working with a lookup table that has, let's say, m bits, the size of that lookup table is 2 to the power of m. So you have an exponential there, and that's what makes it very hard to scale to bit sizes or bit widths beyond 16, for example. So with DWT, as long as you're working, let's say, with fixed point rationals and your function that you want to represent as a lookup table is smooth, which is most of the cases of interest, then you can shrink this lookup table. You can shave off some of the bits, and which means a substantial reduction in the size of the lookup table. and still have an error that is very similar to what you would get with standard quantization techniques, which is just about removing the bits and see what happens. So in essence, you can have, for the same error with quantization, a much smaller lookup table, and therefore it can accelerate the PBS, so to speak, and it can accommodate now use cases that before were not feasible.
Yep. And is it fair to assume that, this, different flavor of TFH using DWT will make sense for something like machine learning, like FHE/ML. However, for something more, let's say, smart contract based, so let's say a DeFi application where you need precision, this might not be a good fit because of some of these approximations.
Yes, that's absolutely a fair statement. So machine learning has certain tolerance for errors, and that's why this is such a good technique that can be applicable to that domain. In other domains where you cannot tolerate the tiniest error, then this is obviously not a good technique because it does incur into certain approximation deviations. So essentially, if you're working with fixed point rationals, which inherently already will incorporate certain errors because you have a finite precision, then this would be a good technique. If you're working with integers and you need perfect integer precision, this is probably not the best technique because you will have some deviations, you will have some errors being introduced.
Got it. Yeah, that makes sense. That makes sense. On this topic, MPC/ML and FHE/ML, broadly speaking, they can both achieve very similar use cases. What are some, differences that you see here?
So let's maybe give it some pluses and minuses. So plus points for MPC would be that in machine learning, this is already computationally expensive. So if you're using FHE on top of machine learning, you're kind of adding more to the bottleneck that is computational complexity. Whereas if you use other flavors of MPC that are kind of that have Achilles heel somewhere else, for example, in communication or in bandwidth, you're kind of spreading a little bit, the problem, so that you're not adding more computations to something that is already bottlenecked by computations. And in that sense, you can find MPC solutions with under certain constraints. So we're talking about small networks, maybe 2 parties, maybe 3 parties, and they can provide very interesting and impressive results. For example, you can run GPT-2 inference on a 1.4 billion parameter model in under 10 seconds per token, or in 100 million parameter model in under 1 second per token. That's something I don't believe is achievable today with FHE. But on the plus side for FHE, those examples that I've given, they also require a lot of pre-computed material, so in the gigabytes per token. So that makes them, not that much production ready as one would expect, because there's a lot of cost, hidden cost behind each one of those token inference processes. And so FHE that has that important advantage that it doesn't require pre-processing. And also, it doesn't suffer from introducing more nodes to the computation. So when you are working with FHE as a building block for MPC, the cost of hiding the private key behind 2 nodes or 10 nodes or 100 nodes is negligible, because that's one operation that takes place when the computation is done, when you have to decrypt. Whereas in MPC, the cost is visible in every single operation that you do, because there is communication going on between all those nodes. So you're going to suffer more from an increased number of nodes than in FHE. So that's kind of, there's pros and cons from each approach, as we were discussing before. There's no silver bullet in any case, and both are currently, in the context of private inference for LLMs, they are constrained by the level of privacy. They can provide passive security solutions, but active security solutions, I think, are beyond the scope of current technology. Just to remember, active solutions were those that are so powerful that even can cope with nodes deviating arbitrarily from the protocol and trying to change the result from the computation. Whereas passive solutions are those that where you get protection against nodes trying to find out about the secrets, in this case, the weights and the inputs to the LLM inference problem. But if they wanted to change the result, they would be able to randomly produce some random gibberish in the end. So we're right now in a position where we're starting to work with passive solutions, not active yet. And in the MPC case, for a very restricted sets of nodes, two parties, essentially.
So that brings kind of the question, what's the path for scaling, Nillion or like MPCs in general here for far out in the future? For FHE, the answer is pretty straightforward. Just hardware acceleration, just improve all the computational efficiency for FHE. But what's kind of like the path for scaling for MPC system?
So I think in general, for scaling the orchestration layer at the language level, it's going to be about incorporating more and more PETs to exploit the optimality of the combination of different PETs for a given problem statement, so that you have more tools in your toolbox to work with and you can find better solutions by just combining them in a smart way. And talking about the network and how it scales, it's about, of course, for those clusters who are heavy on FHE computations, it's going to be about scaling or improving the hardware. For those MPC solutions that are bandwidth constrained, those are actually the easiest ones to scale up, because bandwidth is a resource that can be horizontally scaled. So good news for garbled secrets in that front. And for those that are based on linear secret sharing, which are kind of bound by the number of rounds of communication, the thing is a bit more difficult because you cannot change the speed of light. So essentially, there is very little that you can do on that front beyond just putting the nodes geographically closer so that the round trip times between communications are smaller.
Yeah, you're right. So Nillion with this orchestration, design, it's the path to scaling each of these solutions will be quite different depending on the way they're structured. And as a final question here, anything you'd like to share with your community about any upcoming roadmap announcements, products, or things that they can try today?
Yeah, so I would encourage everyone to go on to Nillion.com and download the SDK and test it. So we have an SDK ready for use. So you can download it. You can use it in your local system. You can write your NADA program, and you can connect to the network through the Nillion client, and store programs and data or secrets and compute on them. And you have like two paths. One is the Python quick start path, so using Python essentially as a client, and the other one is a JavaScript path. So I would encourage people to do that. I would also encourage them to go to Twitter, and I would like them to also kind of finish with a thought on what we said before about LLMs. So we said that currently they're a bit constrained in the ability from the best PETs to run inference on them. But I think there's a number of things going on in the broader picture that actually make it very interesting for PETs to step into this domain. And one of them is that I think the nature of interaction between users and LLMs is going to change from one where we're currently like sergeants, giving instructions and orders to soldiers, which is something that happens very frequently, and we expect to have very quick responses, to one where we're going to be like, presidents giving orders to generals. So where you give more time to the general to come up with a right strategy. So it becomes more independent, more intelligent, and so you're not expecting, the LLM to come up with an answer like in seconds as we do currently, but you do expect the answer to be more, correct and more intelligent. And in this transition, the two things happen. First is that the speed is likely to become a secondary factor. So we will still have, of course, fast interactions in the future, but you will also have these more intelligent, more more complete responses where you can wait more. And the second one is that privacy is going to be more important because the type of orders that you share with a soldier are less sensitive in terms of privacy than the ones you would share with a general. So things are going to get way more personal than they are today. And so PETs are definitely a must-have, I think, in the future. But with, for example, agents, which is a trend in AI, where it's giving more autonomy to the different LLMs by adding different flows, agentic flows, like planning and the use of different tools and so on. So agents is already a step where we're seeing that you get more interesting responses if you let the agent run some thinking on its own, and you can wait a little bit for the answer to come back. And so this is already getting in, closer to that vision where I said we're like a president talking to a general. So yeah, this is like a final thought that although LLMs are like a moonshot right now, I think things are going to play out in a way that actually we're going to need PETs, and PETs are going to be able to answer that challenge and address that challenge.
Yeah, very cool. What's your sort of prediction for when confidential LLMs would be ready?
So I would think we still are like, I don't know, like a few years ago, like a few years away from that point. I think we do have to solve the problem of bandwidth, like in the MPC scenario, at least in the two-party MPC scenario, the pre-processing, all those gigabytes of information that need to be pre-processed per token inference. I think that needs to be reduced a lot, substantially. But if you think about it in terms of speed, like at least for those simple models, GPT-2 with 100 million parameters under 1 second per token. So that's not that far away from like the 4 to 10 tokens per second that would be acceptable already for humans. Humans cannot read more than 3 or 4 tokens per second, so anything faster than that is already interesting. And if you combine that with the agentic flows that make you not have to wait immediately for the answer, but you just give the problem to the AI and then you come back a few minutes later, then it could be like sooner than expected.
Yeah, great. That's a great closing thought here. Yeah, thank you so much, Miguel. I think we covered quite a bit today about FHE and MPC and some other PETs. So yeah, thank you so much for taking time today. It was a pleasure having you here.
Thank you, Remy. Thank you for having me here.